Okay guys, coefficient of determination, R squared this time is what we're doing, which is different to the one we just did, the lesson we just did, because that was Pearson's correlation coefficient R. Now, this one tells us the degree to which one variable can be predicted from another linearly related variable. And it's, as I said, called the coefficient of determination. So we're going to get our R and we're going to square it. And of course, when we square it, we're going to get always a positive number. And because it's less than 1, we're squaring something less than 1, it's always going to be between 0 and 1, all the time. It's useful when we have two variables which have a linear relationship. It tells us the proportion of variation in one variable which can be explained by the variation in the other variable. And it also provides us a measure of how well the linear rule linking the two variables x and y predicts the value of x. Righty, first example says a set of data giving the number of police traffic patrols on duty and the number of fatalities for the region was recorded, and the correlation coefficient of R equals negative, and 0.8 was found. Calculate the coefficient of determination and interpret its value. So this negative means that it's going down. That's what the negative means, it's going down. So if you're looking at a graph of this, you'll get a graph which is going down like that. So it's a negative graph. So to work out the coefficient of determination, R squared, all we have to do is get our R and square it. But we've got to square the whole thing, including the negative. Because remember what I said, it always turns into a positive. So when we square negative 0.8, we get 0.64. Then we can convert it. We can write our little thing there. We can say we can conclude that 64%, because 0.64 times 100, to turn it into a percentage, gives us 64% of the variation in the number of fatalities can be explained by the variation in the number of police traffic patrols on duty. The second example is about carbon monoxide levels in the air and traffic volume, which are linearly related with that rule there, and it's negative 0.985. It says, determine the value of the coefficient of determination, write it in percentage terms and interpret. In this relationship, CO content is the dependent variable. So we get the 0.985, and this time, sorry, it's a positive 0.985, not a negative. And when we square that, and again we're squaring the whole thing, we end up getting 0.97. And turning that into a percentage, we get 97%. So we say, therefore, 97% of the variation in carbon monoxide levels in the atmosphere can be explained by the variation in the traffic volume. Because remember, traffic volume, the more traffic you've got, the more carbon monoxide is going to be in the air, because that's what cars give out. And there's the questions for you.